Okay, so here's a trickier beam now. This is actually statically indeterminate. If this support were not there, this cantilever beam would be able to support the force there. But in addition to the cantilever fixed support over here, I've got this redundant support right there. We actually cannot do this problem without considering deflections because it is statically indeterminate. Okay, again, I set up these guys here so they have variable names. I've set up this actually whole column to have the variable name x. And then I've got my formulas here. Now, if this is the problem, then the distributed load, the only thing that's happening between the ends there is just that guy right there, and I don't know what it is. So I have an unknown r times x minus L over 2 to the minus 1. That minus 1 means this is a force. So that's the only thing that's happening with the distributed load. When I integrate that, I'm going to get r times x minus L over 2 to the 0 plus constant, and then we get raised to the 1 plus that. When I want to get the slope, I actually divide by EI and then integrate, so I get the x squared over 2, and integrate one more time, we get the deflection, so we've got that x cubed over 6 there, plus these constants here. So I need to translate those into Excel formulas. So again, I've got this, I've actually added a fifth unknown here, C1 through 4, and then this unknown here, which I had to unfortunately call underscore r, because for the same reason as a C, you can't actually start a variable name in Excel as C or R because of things that mean column and row. So I've called it underscore r, which is legal. So unknown underscore r times if x greater than L over 2, 1 or 0, that's the step function again. So there's the shear force. The bending moment now is going to be r times x minus L over 2 to the 1. That's r times if x is greater than L over 2, then x minus L over 2, otherwise 0. And plus the C1x plus C2. Theta, I'm dividing by EI now. And I've got now r over 2 times if x is greater than L over 2, that thing's squared, like this. And then deflection, same unknown r, r over 6. That's this quantity raised to the 3, otherwise 0, and then here's the polynomials, and then there's the EI right there. So I've successfully translated those guys from the written down formulas to Excel formulas here. So same thing, I'm going to highlight those guys, double click to copy the formulas all the way down to the end of the beam, and I'm going to use the solver. So tools, solver. Need to get rid of this here. I want to change these 5 guys right here, and I want boundary conditions. Okay, so boundary conditions for this beam. Here I have no deflection. In other words, the beam can't move up and down at the wall. Also can't rotate, so both the slope and the deflection at x equals 0 should be 0. So let's do deflection at x equals 0 equals 0. And let's see, what did I do? Did I do slope? Yeah. So I'm going to add, so I'm going to add now deflection at x equals 0 is equal to 0. Let me check to make sure I did that right. So column D is yes, theta, and column E is deflection. So I got the slope and deflection at the left hand end of the beam at x equals 0 or equal to 0. I'm going to add more boundary conditions now. I know the deflection here has to be 0 because there's that roller sitting right there. So the deflection at L over 2, L is 1, so the deflection at 0.5, deflection is the last column at 0.5, better be equal to 0. And I need 2 more boundary conditions as well. This end has no bending moment because there's nothing to cause that, so that's the bending moment x equals L. Here's bending moment. I'm going to scroll all the way down to the last column, or last number in the column. That's the end of the beam. So that better be equal to 0. That's the bending moment at the end of the beam is 0. And one more boundary condition. Let's see, I don't know what the deflection or slope are anywhere else. I do know the shear force. The shear force there must be F, right? Because that can go directly into the beam. So the shear force at the end of the beam, better be equal to whatever F is. Well, there's F right there. So hit OK, and that should be my 5 boundary conditions. And then make sure that's not checked and hit solve. Yep, it found a solution. It actually found out these values, including that reaction right there, so that the deflection there is 0.